This video is the first in a series on how to choose a probability distribution. Let's begin with our conceptual risk equation. Risk equals probability times consequence. It's clear that if you're going to be doing risk assessment, you're going to have to be able to handle the probability dimension of the risk. Quantitative risk assessment requires you to use probability directly. Sometimes you'll be estimating the probability of an event. What's the likelihood that a flood will strike? What's the likelihood that the hurricane will hit our city? What's the likelihood that your new product will catch on or that the new store will fail? So sometimes you'll be working with discrete probability estimates. Other times you're going to be working with risk assessment models that require you to use distributions. These distributions can be used to describe the data that you have accumulated. They can describe the model variability, particularly when you are trying to represent a range of consequences and their likelihoods. Or you can use a distribution to represent your knowledge of uncertainty about a critical value in your model. In all of these applications, we come down to the same basic question. Which distribution should you use when you need to use a probability distribution? Probability is not only the language of uncertainty, it's also the language of random variables. So let's begin by defining a couple of concepts here. When you're doing risk assessment, you are going to run into a number of values, a number of quantities, and some of these quantities are going to be constants. If you happen to be using the number pi, for example, that's not going to change. If you're talking about the number of production facilities in your company and that happens to be the number 5, that's not going to change. There can be many constants in a risk assessment, but there are also quantities that change their value, and these are variables. Some things vary in a predictable way. I might have a different lunch every day, but if I always have peanut butter and jelly on Monday and tuna fish on Tuesday and egg salad on Wednesday, then once you know the pattern in my variability, my variable is not terribly interesting anymore. It's very easy to predict. But there are also variables that vary unpredictably, and they're a greater challenge, especially for risk assessment. So we're going to call those variables that vary unpredictably random variables. A random variable might be something that is known and predictable by other people who perhaps have a greater understanding of the problem, but a random variable is not known by us. A random variable is a variable that varies in an unpredictable fashion. There are many of my peers and colleagues who would object to the offhand definition of a random variable I just gave you. What we're working for here, what we're working toward, is a comfortable, informal kind of feel for what these values are. So as part of that, I'd like to ask you a question. How many probability distributions can you name without help? There's the normal distribution. But do you know others? Take a second. See which ones you can think of. By the time you finish this course, I guarantee you'll know a good many more. But this would be a good place to think about what you already know about these distributions. And then figure out how would you know which one to choose and use in a risk assessment. There are going to be a number of routine kinds of risk assessments where you will be taking an existing spreadsheet model that your business or your organization uses, and you will be trying to address uncertainty in the calculations that they've already been doing. And in cases like that, it's often a simple thing to go into a cell where there is some knowledge uncertainty or some natural variability, and you'll know exactly what distribution you want to put in there. There will also be times when you are going to be working on risk assessments that are going to be critical to the success of an organization, or they are controversial, or they're going to be highly visible in some public policy sorts of decision. So there will be times when you're going to have to choose a probability distribution very carefully. If you are comfortable with your methods for choosing a probability distribution, and if they are serving you well and not getting you into any trouble, please, by all means, feel free to continue to use them. But if you are concerned about choosing a proper probability distribution for an important risk assessment, then I'd like to offer you some suggestions for how to do that. This was one area where I was a bit perplexed when I began to do risk assessment. How do I know which distribution to use? I never did find a list like the one I'm going to present. I found either very little or very complex kinds of methodologies. And so this strikes a balance in between. And I suggest 9 things that you might do if you have some data. Now, if you have no data at all, we'll talk about that a little bit later. But this discussion is when you have a bit of data and you would like to use a distribution to represent it, what would you do? First thing I would suggest is to ask, can you just use your data? Do you have to bother to call it some other kind of distribution? Maybe we don't have to call it normal or exponential or anything else. Maybe we can just say these are the data. This is the truth. If you cannot use your data, then the next thing you want to do is to begin to understand your variable. Where does the data come from? Is it a continuous or discrete variable? Is that variable bounded or unbounded? Do your data have meaningful parameters? Is it univariate or multivariate? We're going to be looking at each one of these, and that will be the focus. Items 1 and 2 will be the focus of this video. In a subsequent video, we will go to items 3 through 9, and there you would begin by looking at your data. Make sure that you plot it and see it visually. Use whatever theory is available to you. There might be some useful statistics you could calculate to help you figure out what kind of distribution to use. Previous experience, both yours and that of your community of practice, can be very useful. Distribution fitting software has become very easy to use, but it is really one of the last resorts. It's more for verifying what you already think. If we get beyond the distribution fitting step, you might seek some expert opinion. And then finally, there's sensitivity analysis. We will consider each of these in one or more of the videos, and then I will provide you with an overall demonstration of how to apply these in a third video. The very first thing that you need to do is to consider your data. How much data do you have? Where the data come from? And do you need a distribution at all, or can you just use your data? The answer to these questions really depends on the questions that you're trying to answer. Those questions would be specified by your risk managers. And then, of course, it will also depend on the data. If your data are test case data, or if you've just generated them playing around with a simulation, then these might not be data that are suitable for use. However, if they come from a reliable source, then just using your data may be all you need to do, and you can end this process at step 1. If your data are representative of the population that is germane to your decision problem, then you could use them. Let's imagine that I'm building a risk assessment model, and one of the input variables is water temperature. We've seen that that's come up in our Vibrio parahemolyticus case study. So imagine that I have some data. We have some measurements of water temperature. Well, if my data are representative of the population that's germane, I can use them. What does that mean? If I'm doing a risk assessment that is looking at oysters harvested from a region throughout the year, then my data would have to cover the year. The sample would have to be large enough that it would be representative of some of the variation in water temperature that would occur over the course of a year. Even when you have data that are representative of the population, and they're very germane, one of the problems that you might have could be bounding your data. Because if you have a sample, if we have our water temperature sample, what's the likelihood that our sample includes a true minimum temperature for the water in the period of time that we're interested in? Or what's the likelihood that it includes a true maximum temperature? So there may be a need for you to estimate those minimums and maximums independent of the data that you already have. If that's not clear, it will become so in one of the exercises we'll do elsewhere. But keep this in mind. Any data set that you have, any column of numbers in a spreadsheet anywhere on your computer, can be readily converted into a cumulative distribution function or a general density function. So there are two terms that would be useful to become familiar with, because any data can be fed into either one of those functions, and you can have a probability distribution that is independent of any of the families of distributions that we're all well aware of: the normal, the exponential, the triangle, and that sort of thing. You'll have your opportunity to work on this as a class exercise, but I'd like to offer it as an example of how you can fit data to an empirical distribution, as long as you have your data are reasonably extensive. Notice the middle column, I have data values. They have been arrayed from the smallest to the largest. I talked about the difficulty of sometimes bounding your data. You may have to estimate the minimum and the maximum, as I did here. This value logically can't be less than 0, and it's not going to be more than 60. So I provide those values. The other values were observations that I have accumulated. In the third column, the cumulative probability, think of those as basically percentiles. It's an easy thing to create the percentile using that index value in the first column. So if you have some data, and if you rank them from smallest to largest, if you number them, then it's easy to calculate a cumulative probability. With this information, columns 2 and 3, you have now created a probability distribution. We don't have to call this distribution normal or anything at all. We just say these are the data. So please be aware that with any data, whether you have 1,000,000 data points or the 17 that we started with here, you can create a cumulative distribution. There may be times when you can't use your data. They may not be extensive enough, they may not be representative enough. There may be any number of reasons why you're not able to use your data directly in the model. So given the wide variety of distributions that are available to us, it's not always easy to select the most appropriate one. And the results of your risk assessment model can be very sensitive to the distribution choice that you make. If you use the wrong assumptions in a model, it can produce incorrect results. And if we make decisions based on incorrect results, we may be making poor decisions. Poor decisions can have undesirable outcomes. So the stakes are actually quite high here. So what we'll begin in the remainder of this video and continue in the next video is to consider what you do when you're not going to use your data directly, but when you are going to choose a probability distribution to represent your data. As a starting point, of course, you have to understand your data. Presumably, You will already have a decent understanding of your data if you considered using them directly in an empirical distribution. But a place to begin, of course, is what is the source of the data. If your data come from good experiments, or from direct observation, or perhaps from surveys, then you may have data that are very representative of the population that you're trying to model. Perhaps you've gotten data from a computer database, and then it would depend on the data. The United States Bureau of Labor Statistics, for example, makes databases available for a wide range of economic variables, and this would be considered among the best data. In other cases, there are just what should we call them, wild Excel files with numbers in them that can be gathered from the World Wide Web. In that case, your computer database may not be quite as good. Literature searches may reveal some good data. You may find that if you have a good and rigorous model and do some simulations, that the data that result from your simulations provide nice inputs to other models when you have a chained model. In other instances, a simulation may be doing little more than producing garbage in and garbage out. If you have test case data, by test case data, I generally mean I've made up some numbers and plugged them into my model to see if the calculations are right. So if you have test case data, that's really not going to be suitable as a basis for probability distributions. So when we look at our source of the data, you have to make sure that your data are credible. If you have test case data, if you have spurious simulation data, if you have some incomplete information from an article that you read, or a computer database of somewhat questionable background, then you might not even be able to use your data at all. So this is the place to begin. Understand your data. Once you're comfortable with the source of your data, the most important thing that you can do to help you choose a probability distribution is to understand whether your data are a continuous random variable or a discrete random variable. Right here you're looking at the palette of distributions that are available from Palisades at Risk. Blue distributions are suitable for use with continuous random variables. The red distributions are suitable for use with discrete random variables. In general, a continuous random variable can assume any of the possible values that exist over some range or segment of the number line. So the normal distribution runs from positive infinity to negative infinity. So any value at all, any number that you can come up with could be represented or found as part of a normal distribution. Other distributions might only cover the segment from 0 to 1. For example, if we were looking at percentages of fish that have a certain disease, for example, it can't be less than 0% and it can't be more than 100%. But in that 0 to 1 range, any value at all is possible. So continuous random variables are pretty common when we are measuring things, the duration of time, weights, things like that can actually take any value at all, and we're only limited by the precision of the instrument that we're measuring with. Statistics, sample statistics in particular, are also often continuous random variables. A mean number of children in a family could be 2.71463,198, and so on. So know whether your variable is continuous or not. Discrete random variables tend to be things that we count. Whole numbers are common examples. The number of children in a family would be a discrete random variable. But discrete random variables, are not limited to whole numbers. Whenever we find ourselves in a situation where the value cannot assume some values in an interval, you have a discrete random variable. So, for example, in the United States, we use dollars and cents. We mark parts of a dollar out to the hundredths place. Strictly speaking, then, anything measured in dollars would be a discrete random variable, because $17.237,982 would not be an allowable value. And therein lies one of the art parts of risk assessment. You will find that it is handy, not only handy, it's necessary perhaps at times, to treat some continuous variables as if they were discrete, and to treat some discrete variables as if they were continuous. We very often will treat money distributions, monetary variables, as continuous random variables, for example. So you'll see examples as you go through some of the risk assessment courses where people have used a continuous distribution for a discrete random variable or a discrete distribution for a continuous one. When you see those, please feel free to ask questions in class, because there is a little bit of art to this. But in general, for the vast majority of cases, if you have a continuous random variable, you want to use a blue distribution. If you have a discrete random variable, you want to use a red distribution. So get that part right from the outset, and it will make your job of choosing a distribution much easier. After you've determined whether your variable is discrete or continuous, the next thing that you want to ask is, what values are possible for my discrete or continuous variable? And here what we're after in particular is to determine whether your variable is bounded, unbounded, or partially bounded. A bounded variable has a value that must lie between two determined values, usually a minimum and a maximum. So if there is a logical minimum and a logical maximum, for example, if we were talking about what percent of oysters have pathogenic Vibrio in it, it's not going to be less than 0%, it's not going to be more than 100%. So that variable lies between 0 and 100%, or 0 and 1. There is this logical limit. There are other variables that are bounded, but sometimes the bounds are a little fuzzy. Suppose we were trying to determine the weight for an adult human male. We know there's some minimum below which a person cannot weigh. It's something bigger than 0, but what is it? We really don't know. We have to grapple with issues like, what do we mean by an adult, and all those kinds of things. But presuming that we could resolve them, we still have the very clear idea here that yes, there is a bound, but we don't know what it is. And likewise, the maximum, we know there's a bound, but we don't know what it is. Whether the bounds are fuzzy or whether they're very clearly delineated, we would still have a bounded variable here. Okay? An unbounded variable. This theoretically extends from minus infinity to plus infinity. Any value at all is theoretically possible. So when we have a normal distribution, we are usually going to be describing a variable that varies over some relatively fixed range. But you should be aware that at least in theory, the tails of that distribution go off to plus or minus infinity. Finally, we have partially bounded. Some variables are constrained at one end. Let's talk about the size of a rock. It can't be less than 0. If we get very small, we consider a tiny grain of sand. If we define a tiny grain of sand as a rock, it's going to be very close to 0, but it can't be less than 0. But it might go off into infinity. So there will be some values that are going to be partially bounded. And actually there are quite a few. There are many things in nature that can't have negative values. but that can have almost limitless positive values. So what you want to do is identify whether your variable is continuous or discrete, and whether it's bounded, unbounded, or partially bounded. Those two pieces of information are going to help you zero in on a small subset of distributions that would be among the candidates for you to work with. Here are some examples of those subsets. If you're dealing with a continuous unbounded variable, some candidate distributions would be the normal distribution, the t, or the logistic distribution. If you have a bounded continuous variable, you see there a number of candidates, the beta all the way through the triangle distribution. And if you have a continuous variable that has a left bound, usually 0, but no right bound, then there is a different subset of distributions that you may be working with. So it can be very helpful. If you recall the size of that palette we were looking at just a moment ago, these two pieces of information can quickly help you zero in on some candidate distributions. If you have a discrete distribution, one of the first things you probably should know is that there are no unbounded discrete distributions. There are bounded distributions. The binomial is one that you'll know well before you leave this program. The hypergeometric is another. And the choices are relatively small. We also have left-bounded discrete distributions. The Poisson, the negative binomial, and the geometric are three good examples of these. But the point that I would like you to take is simply this. With knowledge of whether the variable is continuous or not and bounded or not, you can quickly zero in on candidate distributions. The next distinction you might want to make about your data is subtle and difficult for many people, and that would be, is my variable parametric or non-parametric? So let me begin by just giving you a couple examples of each. On the left-hand side, we have parametric distributions. These are distributions for which the values follow the form that's readily described by a mathematical function. And this mathematical function has some parameters. And I'll give you an example in the next slide. On the right, we have some non-parametric distributions. This is the uniform, the PERT, the triangle, and that cumulative, the empirical distribution that we talked about at the beginning. So we're going to look at parametric and non-parametric distributions here in just a second. So perhaps we should review briefly this idea of a parameter. A parameter is a constant. It would be a constant in nature. The mean high temperature of Melbourne, Australia in the month of May, that is a parameter. That mean has a fixed value. So that's a parameter. Okay? If our data have parameters, we might be inclined to look at parametric distributions. So let's go to the next slide. Let's begin our discussion by looking at that normal probability density function down in the lower right. This is a function that describes the normal distribution for a variable x. So x is the variable of interest. It would, let's say, water temperature, and it's going to take different values. When we look at that function, we see x appears in there. So that's the variable piece. But everything else in that function is a constant. 1, 2, pi, e. These are all numbers whose values are well known. You'll see two other symbols in there though. The sigma, that's the standard deviation, and the mu, that's the mean. But these numbers are also constants. This is saying, this formula is telling us if you have the mean, the standard deviation, you know what a 2 is and what a 1 is and what a pi is and what e is, then we can plug in these other values for x and we can talk about the probabilities of them occurring. But here's the important part. Where do we get that sigma and where do we get that mu? They come from data. They come from the x values. So if we've got enough x's, we can estimate the mu and we can estimate the sigma. So with that in our back pocket, let's return to the question here. Does your variable have parameters that are meaningful? So if you've got some data, we'd like to know if these data have parameters that are meaningful. Does it make sense to calculate a mean or a standard deviation? And remember, a parameter could be any characteristic of a population. The second biggest value in the population could be a parameter. The means and medians and all those sorts of things are more normal parameters. As you move through your risk assessment career and look at more complex probability distributions, you'll see that there are parameters that you don't have any good intuition for. Alpha 1 and alpha 2 and betas and things of that nature. So we want to know if our variable has parameters that are meaningful. With the parametric variable, the shape of the distribution is determined by the mathematics that describe a conceptual probability model. So in other words, I have some data that happen to be described by that function that you're looking at here. And that's just one function. But that's a function where the parameters really determine the shape of the Bell distribution. There would be other density functions that would have parameters as well. The exponential, log logistic, and many others. To use a parametric distribution, you usually have to have some knowledge of the underlying theory behind either the function itself or the distribution of your data. A non-parametric distribution, one example is the empirical distribution. And we're basically saying, I don't think there's a mathematical formula that defines the shape here. So I work at the university, and if we're saying, what do you think the incoming freshman class will look like? How many students will we have? Well, I might say something like, it's not going to be any less than 170. It won't be any more than 200. And it'll most likely be 186. Notice the data that I have, past enrollments and things, might not be representative of the current generation, the demographics of this generation. So the data that do exist are of limited value in estimating the number that I'm after here. And I'm using a non-parametric distribution. With those three numbers I just gave you, they could describe the parameters of a triangular distribution or of a PERT distribution. And this is where you're going to get confused, because I just said these non-parametric values, the 170 to 200 and most likely 186, I said they're the parameters of a triangular distribution. So where the confusion will come in is we are now speaking in a theoretical world, a conceptual world, where we can divide distributions into parametric and non-parametric piles. But when we step into the world of at-risk and your software and other softwares like that, even when we're looking at non-parametric distributions, like the triangle and the PERT and the uniform, the software will ask us to identify the parameters for that non-parametric distribution. And if that hurts your head, I say that would make you very, very normal. It's confusing, and so you just have to focus, take your time working through this. The non-parametric distributions that we'll use, they're intuitively easy to understand, they're flexible, they're very useful because they're not bound by mathematical formulas that are describing the natural universe. If you decide that you do have a parametric distribution, as opposed to a non-parametric distribution. And let's talk about that normal distribution since we used the function there. You've decided that a normal distribution is what you're after. You know there are two parameters in a normal distribution, the mean and the standard deviation. Well, a probability distribution that has precisely known parameters is called a first-order distribution. So, for example, if we have a normal distribution with a mean of 100 and a standard deviation of 10, we know the mean is 100, we know the standard deviation is 10, that's called a first-order distribution. There will be times, however, when we don't know what the mean or the standard deviation is, and we're going to call that distribution a second-order distribution. So here, using some of the at-risk terminology, you see an example of that. You see we have a risk normal distribution, the parenthesis opens, and the very first argument is telling us what we believe the mean is. And this is saying we don't know what the mean is, but the mean can be described by a triangular distribution with a minimum of 90, a maximum of 103, and a most likely value of 100. The second argument is the standard deviation. And here we're saying that's a uniform distribution between 8 and 11. So a normal distribution with a mean of 100, standard deviation of 10 is first order. A normal distribution with triangular distributions and uniform distributions for the parameters is called a second order distribution. So you would choose a parametric distribution if you have theory that supports the choice of a parametric distribution. If we're working with sample data, the central limit theorem gives us a strong theory to presume that a statistic would have a normal distribution. There can be other theories that come from your own disciplines or from statistics. Not all of them are going to be as rigorous as the central limit theorem, but theory could support the choice of a parametric distribution. A parametric distribution may have already been proven to be accurate for modeling your specific variable. So we might not have to rely on theory. Maybe we know that when it comes to modeling water temperature, a normal distribution seems to work well. You would use a parametric distribution if that distribution happens to match your observed data very well. Another time when a parametric distribution might be desired is if you need a distribution with tails that extend beyond the minimum and maximum you've observed. So sometimes we may have only seen a normal range of variation for a variable, and what we're really interested in, what really becomes important in our risk assessment, are the extreme values that can occur. And those extreme values may not have been observed in nature before. So we need a parametric distribution that will give us an idea how far the tails extend and how thick the tails are in reaching that distance. Non-parametric distributions like the triangle and the PERT, the uniform and the empirical distribution are chosen when you are lacking theory. There's no strong theoretical reason to assume that your variables follow any kind of mathematical model, or there is no commonly used model. You've looked through the literature and the data and find out that there's no consensus on what the distribution ought to be. If you have severely limited data, I just gave you an example a few slides ago, trying to estimate the number of students that would be in the incoming freshman class. And in that case, my data would be severely limited. What we have from the past may no longer be relevant, and so I'm able to estimate a minimum, a maximum, and maybe I can make a guess at which value between those two is most likely. That's a good example of severely limited data. The other instance would be when knowledge about this variable is very limited. We just have some general beliefs about it, and maybe we have a little bit of evidence. So this is where you would choose a non-parametric distribution if you find yourself in this situation. Before we leave this step of considering your data and understanding your data, one thing that you want to ask is, do your data depend on any other variables? Does your variable depend on something else? In other words, are you going to be using a univariate distribution? All I have to do is worry about the distribution of one variable. Or would there be a multivariate distribution, such as you see in the figure there? So a univariate distribution describes one parameter or a variable that's not probabilistically linked to any other variable in your model. Multivariate distributions describe several parameters that are probabilistically linked in some way. So in engineering and ecological relationships, we often find that they are multivariate. The temperature of water and the pH of water are closely related. So you wouldn't treat those as two separate variables if you had an ecological model. Interest rates and housing prices might be closely related. And if you were concerned with both of those in a risk assessment, you might have to deal with them in a multivariate way rather than a univariate way. This is a summary table that you'll find in your textbook, and it provides actually a very nice summary of what we've been talking about here, because you can see, depending on the answers that you get to the questions we've been posing here about whether my variable is discrete or continuous, whether it's bounded or not, and so on and so forth, that will narrow down your choices of a distribution very rapidly. So what looks like an overwhelming task initially, trying to figure out which distribution in that palette should I be using, it can become much more simple, much more straightforward if you follow a systematic approach. In the next video, we'll continue with the checklist to see how you might choose a probability distribution for your risk assessment.